Thank you, Jim, and good morning, everyone. I'm not used to being a warm-up act, but I will do my best to fulfill that role. As Jim said, I've been asked to give you sort of a brief introduction and overview of how we got to where we are today in terms of performance-based design. I think he asked me to do that because I remember so much of it. First of all, what is performance-based design? I think the best definition of performance-based design that I'm aware of was one developed by the SEOC Vision 2000 Committee in a 1996 report. Many of you probably don't remember that anymore, but it really was a landmark report. It was a committee that SEOC put together after the Northridge earthquake. Was funded by the California Office of Emergency Services and the Federal Emergency Management Agency, with the hope that SEOC would develop this new approach to design of buildings that would enable buildings to be developed that would be less susceptible to damage. FEMA's interest in that, of course, was that they end up being an insurance company of last resort, and after Northridge they were sort of tired of picking up the repair costs associated with earthquakes. So they were hoping SEOC would come forward with this new design procedure for buildings that would result in buildings they wouldn't have to repair after future earthquakes. SEOC's take on what performance-based design was or should be are procedures that enable the design and construction of buildings that will reliably be able to attain desired performance, where performance was measured in the very types of terms that were discussed in the SEOC Blue Book of the era, which was the commentary to the then Uniform Building Code seismic requirements. So it talked about protection of life safety, potential damage resulting in loss of occupancy of a building, and potential repair costs. So these were things that people were very concerned about in the 1990s. We recognized that our then current design procedures were not capable of delivering very well what our expectations might be with regards to these performance impacts, and SEOC said performance-based design is a procedure that should be able to allow you to reliably achieve certain tolerances and limits on the amount of losses that actually occur when earthquakes affect our buildings. Now, the original intent of FEMA and others who funded the SEOC Vision 2000 Committee and other performance-based design development efforts was to enable engineers to design buildings that perform better than typical buildings designed to the building code. Again, FEMA was interested in this because they didn't want to be an insurance company and pick up the costs of repair. It turns out, and as you'll hear on and on today, the more common use of performance-based design today is not actually for better performing buildings. Most owners and developers, it turns out, are not really interested in better performing buildings. Earthquakes, though they cause lots of damage and lots of trouble to society, even in places like San Francisco, Los Angeles, and Seattle, occur relatively infrequently. During our practicing careers, we may see 1, 2, or perhaps 3 earthquakes of significance over our lives. The buildings that we design, many of them will never see an earthquake. Developers understand this. They understand the likelihood that their buildings will actually experience an earthquake while they own them, which in the case of high-rise buildings is typically a very short period of time, is small. And so they're not interested in better performing buildings. What they're interested in are buildings that will perform at the absolute minimums that society will allow. And what the absolute minimums that society will allow is what is written in the building code. And so what developers of high-rise buildings are typically interested in is buildings that will perform as well as a building that conforms to the building code, even though the building itself may not actually conform to the building code. So that is the biggest use of performance-based design today, and it is what we'll be talking about throughout the day. But going back to the original definition of performance-based design and what the process is, what it is, how it's intended to work, it starts with a decision maker, and there are a number of different decision makers. It could be the developer, it could be the building official, it could be lenders, it could be insurers, it could be an anchor tenant in a building. But some decision maker or groups of decision makers decide that they need a building to perform in a certain way. And they're going to define this performance in terms of how well they want to protect life safety. And most decision makers will say, that life safety is an absolute, has to be protected at all costs. It's intolerable to have buildings that will collapse and kill people. Interestingly, our building code today doesn't deliver that performance. We claim that what we're doing in our building code today is designing only such that there's not greater than a 10% chance that if you see maximum considered earthquake shaking, your building will collapse. Most of us hope that our buildings will do much better than that, but that's what the building code has as an expectation. Decision makers typically would want something much better than that, whether we can give it to them or not. Some decision makers are interested in minimizing potential repair costs. Many decision makers are interested in minimizing disruption of use, because the real costs of an earthquake are not necessarily repairing a building after the event, but it's the fact that you can't do what you use the building to do on a normal basis while the building is being repaired. And that actually has put a number of businesses in California out of business, and in the state of Washington as well. So it's a very important consideration. After the decision makers decide how it is they want their building to perform in future earthquakes, then it's up to us, the engineers, to figure out how to develop a design that will meet those performance objectives. And I'll be telling you about the process that we have used for that over the years, and then we'll get into, with later speakers, the process that's being used to do that for tall building design today. Now, performance-based design is an alternative to code-based design. Most of what we do when we design buildings, even tall buildings, is largely code-based. Even the performance-based aspects of tall buildings that you hear about today regulate only a very small portion of the design. Most of the design of these buildings essentially conforms to the building code. So when we design a building to the building code, what are we doing? Well, the building code is an ever-growing thick book of rules. And basically, if you boil the rules down, what those rules tell us is that for earthquake resistance, your building has to have minimum acceptable lateral strength and stiffness. Has to be strong enough to resist design-based shear forces, can't deflect or drift laterally more than a certain amount when you apply those forces to a model of the building. It very rigorously specifies how we have to detail our buildings, how the reinforcing steel has to be bent and placed in concrete elements, how we weld pieces of steel together with thickness ratios of elements of steel, how many hold-down type devices we have to put on a wood shear wall building. All of that is carefully regulated in terms of detailing. And then it tells us that we have to attach all of our non-structural components, ceilings, light fixtures, exterior cladding, so that they will not be detached from the building under design earthquake shaking, and so that they'll be able to tolerate the drift that we anticipate the building will experience under design earthquake shaking. So it's a bunch of rules, basically a cookbook. Follow these rules, and you have a code-conforming building. And if you follow all of those rules, then it's presumed that your building will be capable of acceptable performance, and you can find out what acceptable performance is by reading commentary to the code. But the fact is, when we design a building to the building code, we follow the rules, we presume our building will be capable of performing well, we never actually check to see that the building will be able to perform in that way. We just check to see that the building conforms to all of the rules, and it's presumed that it will perform okay. In fact, when we follow the rules, the building isn't always capable of performing okay, which is one of the reasons why every 3 years we end up having to change the rules. Because in part, we see the way real buildings perform in earthquakes. We identify things in the current set of rules that are inadequate, and we invent new rules to fill the gaps and see that we can better get buildings that will perform as we desire them to. Performance-based design for seismic purposes was really born in the period 1971 to 1994, which in California at least was a period of unrest. For those of you who recall that period, during the period 71 to 94, California was experiencing a magnitude 6 or greater earthquake about one time every 18 months, starting with the 1971 San Fernando event. The 1970s, 1980s were a period of great growth and development in California. In the Santa Clara Valley, south of here, the semiconductor industry, high technology industries were growing. And they were doing so, they were booming, growing in very cheap buildings, mostly tilt-up buildings constructed for $35 a square foot. In the Los Angeles basin, the aerospace industry with the space program was growing, and not surprisingly was growing and putting very high value inventory in the same types of very cheap buildings. And when these earthquakes came along every 18 months or so, they caused a lot of damage, and they caused a lot of business interruption, and it caused a lot of consternation among tenants of buildings and building owners. And building owners began to ask engineers how their buildings would perform in future earthquakes, because they heard of competitors in their industry in Northern California or Southern California who suffered significant business losses as a result of earthquake damage to their facilities. And then, after they asked us how their buildings would perform in future earthquakes, they began to ask us to actually design or upgrade existing buildings so that they would perform better. And this was really the birthplace of performance-based engineering. Owners asking, how will my building perform? Oh, that's not very acceptable. What can you do to make the building perform better? And owners typically would express their desires in terms of a series of performance objections. They say, I want my building to be safe. Well, if an owner comes to you and says, how will my building perform? And you say, well, I think this building could collapse in an earthquake. And the owner says, that's not acceptable. I want my building to be safe. In the 1980s, what would we do to get that person a safe building? Well, we had no guidelines for existing buildings in those days. What we had in those days was the building code. And we all knew the building code was very conservative. And so if what the owner really wanted was a building that would be life safe, we said, well, maybe you don't really have to conform to the building code. Maybe it's all right if we just upgrade the building so it has 75% of the strength of the building code. Never mind that the building code assumes that your building has certain prescriptive detailing requirements that it conforms to. Never mind that many of the buildings we were looking at and being asked these questions about in the 1980s didn't have any of these prescriptive detailing requirements because they were built in the 1950s and 60s before those requirements existed. We decided that 75% of current code was good enough for life safety, and that's what we went about doing. Some owners would say, well, this is a very important building for me. This is my corporate data center. If this data center goes down, I'm going to be out of business for a long time. I'm going to lose all my records on who owes me what money. It's be a disaster. I have to be able to get right back in and use my building immediately after an earthquake. Well, what are we going to do about that? Again, this is in the 1980s. Well, the answer to that was, again, easy. Because we knew we designed essential facilities under the Uniform Building Code using an occupancy importance factor of 1.5. And we always went around telling our clients who owned hospitals, fire stations, police stations, that they were essential facilities, and we were designing it with an I of 1.5, and that was going to get them immediate occupancy. So if Boeing came to us, or Lockheed, or Hewlett-Packard, and said, I need to be right back in this building and using it immediately after an earthquake, no problem. We just use the essential facility criteria in the building code and upgrade the building to that. And then around the late 1980s, a rather strange phenomena occurred, and this was the PML phenomena. What started to happen largely as a result of all of the earthquakes that had occurred over the prior 20 years, and all of the lenders who had ended up owning damaged buildings that they didn't really want because the owners of the buildings walked away from them and left the mortgage holder with the building. The lenders started to say, if I'm going to give you a mortgage on this property, I want you to get a seismic evaluation report for this property, and I want that evaluation report to tell me that there will be a probable maximum loss for this building of 20% or less. And if you pass this test of having a PML of 20% or less, we'll give you a mortgage. If you don't pass the test of 20% or less, maybe we'll give you a mortgage, but we're definitely going to require that you have earthquake insurance. And if your PML is really large, like maybe greater than 30%, no mortgage for you, no matter how much insurance you get. So that when that phenomena occurred, owners started asking engineers, please upgrade my building so I will have a PML of 20%. Well, that was a real head scratcher for engineers at that point. we really didn't know what factor we should put on the Uniform Building Code of the era in order to get a building of 20%. And some engineers would put a 1.25 on the Uniform Building Code. Some engineers would stay with the 0.75, figuring that life safe was equivalent to a PML of 20%. But the fact is, if you went to 10 different engineers and asked them to retrofit the same building to a PML of 20%, you would get 10 very different designs. This was not a very satisfactory situation, either for engineers or building owners or for the Federal Emergency Management Agency. And so in the early 1990s, FEMA funded ATC to develop a pair of landmark projects. One of them was the ATC 33 project, which ended in the eventual publication of FEMA 273-274, Guidelines and Commentary for Seismic Rehabilitation of Buildings. And the other was the ATC 40 document, Seismic Evaluation and Retrofit of Concrete Buildings. Very similar documents, really developed by the same people under two different budgets, slightly different teams of people, so slightly different methodologies. But basically, as an engineer, if you could do one of these methodologies, you could do the other. And these were really the first true performance-based design standard-like documents that were available to the industry. Today, they're both embodied in ASCE 41, the Seismic Rehabilitation Standard. And this really forms the basis for performance-based engineering practice today. And much of what you hear about today, whether the designs are conducted per the PEER documents or the LA Tall Buildings Council document, really their technology that they're using is the ASCE 41 technology, developed in the mid-1990s for the ATC 33 and ATC 40 projects. That technology uses a standard process for doing performance-based design. It starts with selection by the decision makers of a series of performance objectives, statements of how the building should perform in future earthquakes. Then the engineer performs a preliminary design. Next, the engineer goes through a process of assessing what the performance capability of that design is. They do an analysis, they check the analysis against acceptance criteria, and decide whether or not the building is performing adequately based on various design parameters. If the building is not performing adequately based on that analysis, you revise the design, you perform the analysis again, you again ask yourself the question, are all my demand capacity ratios acceptable? And you repeat that process until the answer is yes, or the owner says, I can't afford this anymore, and changes their performance objectives. And at some point, you stop doing the iterations, and the owner accepts what you have in the way of a design as meeting his budget, and you can finally go to construction on the project. Selection of performance objectives. Performance objectives have two parts. There's a specification of a design earthquake level, typically done as some earthquake motion that has some probability of exceedance in 50 years. 10% 50 years is a common one, 2% 50 years is a common one, 50% 30 years is a common one, but generally we select a ground motion with some probability of being exceeded. And then you accept a performance level that you want your building to be able to meet or exceed, given that it experiences that level of earthquake shaking. The ATC 40 and ATC 33 projects defined a series of standard performance levels that are with us still today. They're operational, immediate occupancy, life safety, and collapse prevention. And generally these performance objectives are formed by an owner saying, I want life-safe performance for a 500-year earthquake. I want collapse prevention performance for a 2% 50-year earthquake. I want immediate occupancy performance for some other earthquake. And then we go off and do our analyses and check whether or not the building is actually capable of doing that. If you look at these various performance levels in the form of a pushover curve, and remember that ATC 40 and ATC 33 were performed in the mid-1990s, and while structural engineers knew about nonlinear dynamic analysis in the mid-1990s, it was not something that we regarded as practical for use in practice. In fact, in the mid-1990s, most engineers didn't know anything more than linear analysis, and we thought response spectrum analysis was really high tech. And earthquake engineering snobs would turn up their noses at those firms that were doing equivalent lateral force analysis because they weren't doing this high-tech modal response spectrum analysis. Nonlinear analysis was not something that was done. So ATC 30 and ATC 40 introduced the concept of nonlinear analysis with the concept of pushover analysis. It was deemed that the really high-tech engineers of the late 1990s would be doing nonlinear static or pushover analysis. And these performance levels were basically put together as if your building is at a certain point on a pushover curve being a manifestation of how much shear force goes into the building at given levels of displacement. Depending where you are on that pushover curve, you will be in one performance level or another. The process for doing analysis has evolved a lot in the last 20 years. Nonlinear static or pushover analysis is not done very much anymore, even though most of the software that we use is capable of doing it. These days, the software we use is also capable of practically doing nonlinear response history analysis, and that's what we do usually today. And all of the tall building design is done that way. So when we're doing a performance-based design, we build a model in our favorite software. We subject the model to simulations or recorded earthquake histories. We simulate the performance of the structural frame to those recorded histories. Interestingly, when we do this today, we are using representations of the hysteretic performance of the elements that were really developed back in the mid-1990s, and we're thinking static analysis. We only represent, as I'm sure Greg Deerline will tell you later, we only represent cyclic strength and stiffness degradation effects very approximately. We don't do it correctly. But we use these hysteretic relationships that were developed from pseudostatic cyclic testing of elements. People developed backbone curves shown in the lower bottom left-hand corner there to represent the hysteretic behavior of elements. We dump those relationships into our model, we subject them to an earthquake, and then depending on how much nonlinear deformation we get, we try and figure out how much damage is occurring in these elements based on laboratory data that's been gathered over the past 30 or 40 years or so. Performance-based design today doesn't consider non-structural performance, which when you think about it is pretty strange. If you look at the losses that actually occur to buildings, something like 60% of the economic losses are not attributable to damage to structural elements, assuming the building doesn't collapse. It's a result of damage to non-structural elements, ceilings, light fixtures, all of the things that you need to actually use a building. And current performance-based design procedures, they don't ignore non-structural performance, but they are not performance-based. If you look in ASCE 41, the procedures that are contained in ASCE 41 for non-structural design are the same as the procedures in the building code. They're prescriptive. And in fact, when people are doing performance-based design of tall buildings, they're following those same prescriptive procedures generally for the design of non-structural components. What we're here to talk about today is not the past or the present, but really what's happening in the future. The two documents that you see here, the Peer Tall Building Initiative Design Guidelines for Tall Buildings and the Los Angeles Tall Buildings Council Design Criteria, Alternative Design Criteria for Tall Buildings, are the basis for how most tall buildings in the western United States have been designed over the past 10 years. In fact, I can only think of one tall building that has not been designed that way in the last 10 years. These documents take, as Farzad will tell you in a few moments, the ASCE 41 methodology, and they extend it specifically for use in tall buildings. They are definitely about performance-based design to obtain equivalent performance to what you would get out of the building code. They're not about getting better performing buildings. However, as I and other folks and speakers in the room will tell you today, even though what the developers want are buildings that will perform as well as, not any better than, but as well as a building designed to the building code, we in fact believe that these buildings we're designing using these procedures will perform better than buildings designed to the building code, because the analyses that we're performing are much better able to predict how the buildings are likely to respond. than the modal response spectrum analysis used in the building code. We're actually thinking about the performance of the buildings and attempting to look at it and check it. And so we think there's a significant likelihood that these buildings will perform better than buildings that are just designed using code-based procedures.